Hey, my name's Josh Garrick. Going over today, I'm talking about topics in Chemistry 1310. Specifically, we're talking about the formation of ions, really cations, anions, and just regular ions. So we're just going to go through a couple slides with a bunch of information on them that is pertinent and will hopefully help. So starting off with the formation of cations. We know that metals in the S and P blocks have low ionization energies and form cations with Np6 electronic configuration. This pretty much means that large jumps in ionization energy occur when removing an electron from these different ions. Just a fact to know, cations are smaller than their corresponding neutral atoms. Losing electrons reduces electron repulsion, and remaining electrons are more tightly bound to the nucleus. So pretty much cations are the positively charged ions from a metal in the S and P blocks. So that's what we're saying here. To go into more about cations, we know that transition metals can form cations with more than one possible charge. They must first lose an electron from the S subshell, and additional electrons are lost from the partially filled d orbitals. Half-filled d orbitals are set in a fairly stable arrangement. Here's an example in Fe2 and Fe3+. They're both stable. So those are transition metals that work as cations. Looking again, now we can talk about the formation of anions, which is opposite of cations. These are the negatively charged ions, which means they're actually gaining electrons. So nonmetals have negative electron affinities and are generally form anions with an Np6 electronic configuration. They are larger than their neutral atoms, while cations are smaller, and gaining electrons increases the repulsion, and valence electrons are less tightly bounded to the nucleus in anions because they are gaining more electrons, more and more electrons. So these are opposite of what we just talked about in cations. Here's a little chart of the formation of ions and sizes of those ions. So pretty much the positively charged cations can be seen in these three. These two over here would be representing the negatively charged anions. So as you can see, the size is increasing. Size of ions compared to, and this is the size of ions compared to corresponding neutral atoms. Okay, so moving forward a little more, just some more information we have. Cations decrease in size from left to right across the periodic table, as seen in that chart before, was really showing that off. And anions decrease in size from left to right. The number of protons increases from left to right, and electrons are held more tightly from left to right across a period, resulting in smaller ions. So that's moving from a cation to an anion, whether it's positively charged cation or negatively charged anion. You just want to remember that. Positive cation, negative anion. Negative gain electrons, positive lose electrons. More in the formation of ions, the energy released in forming a NAF can be calculated. So here's an example of that. First, the ion pair must be formed. The ionization energy from sodium is 496 kilojoules per mole, and the electron affinity of fluorine is 328 kilojoules per mole. So totally you subtract the two, and that's going to give you 168 kilojoules per mole, which is the energy released. Second, the potential energy from the Coulombic attraction is calculated using the ionic radii to calculate V. So V is equal to negative 591 kilojoules per mole. And the energy released from the Coulombic attraction is much greater than the energy required to form the NaF, the sodium fluoride ion pair. And this is the formation of NaF ionic bond release energy. To talk a little bit about ionic solids, ions are arranged in crystal lattices. So ions experience attractive and repulsive interactions in 3 dimensions, and the strength of interactions decreases with distance. So those were metals and non-metal. These are actually talking about ionic solids now. So moving on a little more with this chart, here we have more about the formation of ions. In this chart to the, I guess to your left right here, we have, or to your right, sorry. Black lines show attractive forces between first nearest neighbors. So these are the black lines here, the first nearest neighbors. Red lines show repulsive forces with second nearest neighbor. So we have these. Blue lines show the attractive forces with third nearest neighbor. Here we go. And fourth nearest neighbor interactions are and higher are not indicated in the figure because they're not as important. In a solid lattice, any given ion experiences a large number of attractive and repulsive interactions with other ions. And that's pretty much what this is trying to show you, that there are that many different attractive and repulsive interactions going on all at the same time. Last little note about the formation of ions. The lattice energy is the overall result of the attractive and repulsive forces a crystal contains. Small ions with large charges from ionic compounds with large lattice energies. Large ions with small charges forms ionic compounds with small lattice energies. So this is just talking more about lattice energies and exactly how they interact and how they work in different crystals. So that's just a little conceptual information. It's not as practical, but well, you're probably going to get tested on this material, and it's good to know about ions and how they work in chemistry. So I hope that helps a little bit.